Now here's a classic example of why angular accelerations and angular velocities are very important. And of course, they're more important in an amusement park ride. So rotor is an amusement park ride where people stand against the inside of a cylinder. Once a cylinder is spinning fast enough, the floor drops out and people still stick to the floor, stick to the wall. So the question is, what force keeps the people from falling to from the bottom of the cylinder? So here, take a moment, think about it, and think about Newton's laws and all the forces that are acting on the people while they are in that ride. So go ahead, draw them yourselves, and then I'm going to go to the board and I'm going to try to draw them myself. So, if I was to assume that the person is standing here and he's stuck to the wall, right? And the rotor is spinning around and around and around. So that means that I have a center-seeking force, the centripetal force pointing inwards, right? It goes inwards that way and it goes inwards that way. And this is the person that I have. He's standing like this, okay? Now, what are all the forces that are acting on him? Well, there is always going to be a force of gravity, which is pulling him downwards, mg, and friction that pulls him upwards, right? Why is frictional force upwards? The frictional force, remember, always wants to point opposite to where the object is going, or even wants to go, right? So that's what's stopping him. So if left to its own devices, if there was no friction, this object would slide down, right? This way, friction prevents it by acting opposite to its sliding force. So the answer to that question, what force keeps the people from falling off the bottom of the cylinder, is absolutely friction. Friction is the only force that's causing them not to move, right? Okay. Now part B. If mu is given to be 0.4 and the cylinder has a radius of 2.5 meters, what is the minimum angular speed of the cylinder so the people don't fall out? So note, it's giving me nothing else except for these two numbers. And it's expecting me to be able to figure out what I need to do. So in order to solve problems like this, we are going to go back to our Newton's laws, okay? So Newton's law says sigma fx and sigma fy. Okay? Write down all the forces that are acting on this person along the x-axis. Okay? Let's suppose we call this to be our positive x and this to be our positive y. Why? Because that's just what we've always done. Okay? So that means I have frictional force here. Do I have a normal force? Yes, absolutely. Since this person is touching at this point, I have a normal force that is acting on this. Where does frictional force go? Where does the centripetal force go? Does it go here? The answer is no. This is actually, your center-seeking force is actually the sum of your forces. So you can't put it on this side, on the right side. So on this side, you will only have minus n. Is this correct? Is my frictional force along the x-axis? Absolutely not. Wrong. Now what happens? This goes here. It's plus frictional force minus mg. Okay? Now what about the motion in the y direction? There is no motion in the y direction. What about the motion in the x direction? Absolutely. The resultant is mv squared over r, which is your center-seeking force, the centripetal force. Okay? Now solving further, from my equation 1, what do I have? mv squared over r equals minus n. From my equation 2, I have fs equals mg. Okay? I know fs equals mu n equals mg, right? That means I can plug this value of n here. Note, I also forgot that the fact that this is going to be minus, right? So this is going to be minus, minus, minus gets canceled. Okay. I can plug this value from here into here, so I get a mu mv squared over r equals mg. M's go away, and I have mu v squared over r equals g. Okay, what was it asking me? It's asking me what is the minimum angular speed. This gives me linear speed, but I know the relationship is v equals r omega. So I can just simply plug this value in here, and I get mu r omega squared equals g, which implies omega equals g over mu r square root. And I know g is 9.8. Mu is 0.4, and r given is 2.5 square root. So do the quick calculation, get your calculators out and do this calculation and come up with what should my omega be. I calculated to be 3.13. And what are the units going to be? Radians per second. Not meters per second, radians per second, because we're talking about omegas, right? So they can't be radians per second. Now here's a really good question. A coin is placed on a record that is rotating at 33.3 RPMs. If mu equals 0.1, how far from the center of the record can the coin be placed without having to slip off? Okay. Now here's a question. It says 33.3 RPMs. That means it's revolutions per minute. What did we say? As soon as you see the word revolutions per minute, convert. Convert to radians per seconds. Okay. So we're going to have 33.3 RPMs, right? So it's 33.3 revolutions per minute. And I have to convert it to radians per second, right? So that means I have to multiply it with minutes over seconds, because I want the seconds to come at the bottom. And I know how many seconds in a minute? 60. So that gives me 1 over 60. And then I have revolutions. So I need to get rid of revolutions. Revolutions per radians. So in one revolution, there are 360 degrees, which means it is 2 pi radians. In one revolution, there are 2 pi radians, right? So that means my minutes will go away, my revolutions will go away, and I will have 33.3 times 2 pi divided by 60 radians per second. And this is the unit I was looking for, right? So my omega is now redefined in terms of radians per second. So plug it into your calculator, see what you get. So I get 3.5 radians per second. But don't trust me, use your own calculators. Okay, now having said that, so that's part one of our problem. So instead of writing the 3.5 radians per second, I have just converted it into revolutions per minute. I've converted it to 3.5 radians per second. So now let's come to the actual problem. It says that there is a coin and there is a record, and I need to define my axis of rotation. So this is going to be my axis of rotation. This is going to be my x-axis. Okay, and I need to place a coin at some distance away from the center. Okay, and it's saying what should the R be so that it doesn't slip. Okay, now as always, what we're going to do is we're going to start by drawing the free body diagram. So this coin is resting on top of the record. It should have a normal force N, and it should have a mg that points downward. Since this is going around in a circle, it will have a center-seeking force which is pointing inwards. And also, because this thing wants to fly out, the frictional force will be inwards. Okay? So then let's write the force equations as we always do. There's going to be two of them, sigma fx and sigma fy. Sigma fx is going to be equals to minus f, because it's pointing that way and I chose my x to be pointing this way, and fy will be n minus mg. There is no acceleration along the y-axis, but this one will become mv squared over r. Okay? So from equation 1 and equation 2, I get mv squared over r equals mu n. Note I'm skipping a few steps. This is now also going to be minus, so minus gets cancelled with minus, and I come up with this as an answer. And n equals mg. That n I can plug back into here, so equation 1 now becomes m r omega squared divided by r. I'm placing the value of v in here, equals mu mg. M gets cancelled, r gets cancelled. I have r omega squared equals mu g. Okay, this means I'm looking for r, which is equals to mu g over omega squared. This question gives me mu equals 0.1. I can plug that in here. It's 0.1 times g, which is 9.8, divided by omega, which was 3.5 radians per second, right? Plug all of these numbers in, come up with an r in meters. My r comes out to be 0.01 meters. Actually, it comes out to be 0.8. So, yeah.